Okay, so welcome back to science class, and now we will continue from where we had stopped in our last class. We were talking about work and energy, right? So we had talked about what is work and seen that work is a scalar quantity, as well as we looked at energy and defined it as a capacity to do work. We had seen its different classifications, and now in this class we will continue with the topic energy, and we will talk about mainly kinetic and potential energy, and after that we will look at the rate of doing work, and mainly our focus will be on the topic energy. Now we may cover the rate of doing work in the next class. So let us talk about the first type of mechanical energy, which was kinetic energy. But before we go into what is kinetic energy, let us recall the questions which we had asked you in the last class. How does a bullet pierce the target? Or how does the wind move the blades of a windmill? Do they have some energy while they are in motion, which gets transferred while steering the target or while moving the windmill? So you can see these moving entities must possess energy, right? If they are not having energy, how will they pierce the target, or how will they move the so much heavy windmill, right? How will they move the blade of the windmill? So these moving entities must possess some energy, and this energy possessed by an object due to its motion is called kinetic energy. Or we can say that when a body is in motion, the energy which it has is kinetic energy, and by the word kinetic we mean something is actually in motion. The word kinetic means something is actually in motion. So kinetic energy is the energy which is associated with something in motion. So you can see the kinetic energy of an object can increase with its speed. Like if we shoot the bullet with a higher speed, it will pierce the target to a greater extent, right? Why? Because when we are shooting the bullet at a higher speed, we are actually giving it sufficient energy, sufficient kinetic energy, so that it can go to the target and pierce deep into it, right? Or when the wind is moving faster, it has more kinetic energy, and therefore it is able to move the blades of the windmill at a faster rate. Now if we want to quantize, or now if we want to measure what is the actual value of energy that they have, like we had found out the value for work, right? We had found out the value for work which an object does when a force acts on it, right? And now we want to find out the energy, the value of energy which a body has when it is in motion, or we want to find the value of kinetic energy. For finding this answer, we must know that the kinetic energy of a body moving with certain velocity is equal to the work done on it to make it acquire that velocity, or the kinetic energy, or the energy with which the object moves is actually the energy is actually the work done on it to make it move at that velocity. Or when you are hitting a ball with your hand, what you are doing, you are actually doing work, you are actually transferring energy from your body to the ball, and now the ball moves and it has kinetic energy. So you can see the work done on the body to move it and to make it move at a particular velocity, that change or that work done on that body is actually the kinetic energy of that body, right? The work which we are doing on it gets converted into the kinetic energy of the body. So let us find out what is the value of kinetic energy, or rather the formula by which we can calculate the kinetic energy for any object moving with a particular velocity. So let us consider an object of mass m, as you can see here, moving with a uniform velocity u. Initially the object was moving with a uniform velocity u. Now a constant force F acts on it in the direction of its displacement, right? It was moving in this direction, and now a constant force is acting on this direction, the same direction, and it is making it move a bit further, which it would have moved if it was at the same velocity u. The F force is making it move a bit further, and the force acts during the displacement s of the body. The object, during the force is acting, during the time when the force is acting, the object moves a displacement s, or the force acts on the body constantly through a displacement s of the object, making it attain an acceleration a and a velocity v. You can see that the velocity has changed from u to v, right? Now we have a different final velocity, and when we see a change in velocity with time, we can tell that there is an acceleration associated with it, right? So the force acted along a displacement s, and it had made the body attain an acceleration a and the final velocity v. So work done can be shown as F into S, right? And what is the force? Force is actually equal to the mass into acceleration of the body, right? The formula we had learned in the laws of motion. Force was actually mass into acceleration. So here we write mass into acceleration in place of F, and now let us see how we can replace S. We know from the laws of motion v square minus u square equals 2as, right? This was the third equation which we had talked about, and now we can write S as v square minus u square by 2a. So you can see we have got a quantity to replace S, and what we do, we put this value of S in this equation. So we get work done equals mass into acceleration times v square minus u square divided by 2a, and you can see this a cancels out, and we multiply the terms and separate them out, and after that we get half mv square minus half mu square. So you can see it is difference of two terms, right? Work done here is the difference of two terms. The initial case, which we can tell by seeing that it involves the initial velocity, and the final case because it involves the final velocity, right? Now what we had got as half mv square minus half mu square. Now if the body had started from rest, or u equal to 0, or when the body did not have any energy, when it was at rest it did not have any energy, right? It was just standing at one place. So we can replace u with 0, and work done will be half mv square only, or we can say that the entire work done on the body which had occurred had been entirely converted to the kinetic energy of the body, right? The entire work done on the body to make it move to a velocity v had been converted entirely to the kinetic energy of the body. Or in other words, we can say work done is equal to the change in kinetic energy of an object, right? Initially the object was at zero velocity, or it was at rest, or its kinetic energy was zero, right? And finally the energy it has is half mv square, and this change in energy had been caused by the work done on it. So this is actually the kinetic energy of the body, right? Initial kinetic energy must be zero, and final kinetic energy, which is actually the entire energy of the body, is half mv square. So this change in kinetic energy is actually the work done on the body, right? Therefore we can easily say kinetic energy is half mv square, right? You can see here Ek, we have named kinetic energy as Ek in short form, and we have written kinetic energy equals half mv square. You can see kinetic energy possessed by an object of mass m and moving with a uniform velocity v can be easily written as half mv square, right? So this is the equation for kinetic energy, or when a body is in motion, the energy it possesses can be given by half mv square. And you can easily see when the body is at rest or v equals 0, kinetic energy is of course 0. And also kinetic energy increases when v increases, right? So let us solve one question using this equation, or rather formula. An object of mass 15 kg is moving with a uniform velocity of 4 meter per second. What is the kinetic energy possessed by the object? Ek, or the kinetic energy, can be given as half mv square, right, at any point of time. So half into m, which is 15, into v square, which is 4 square, comes out to be 120, and the unit, as we are calculating the entire thing in SI unit, we must also get the answer in SI unit as well, 120 joules, right? So the kinetic energy possessed by the body, which is of mass 15 kg and moving with a velocity of 4 meters per second, is 120 joules. And kinetic energy, as it is also an energy, it must be also a scalar quantity, right? Energy is also a scalar quantity like work, because in the last class we had seen energy is equal to work. So let's do one more question. What is the work to be done to increase the velocity of a car from 30 km per hour to 60 km per hour if the mass of the car is 1500 kg? Now we have seen that the change in kinetic energy, right, if a body has some initial kinetic energy and if we are doing some work on it, its kinetic energy increases, or the difference in these kinetic energies, the final kinetic energy and the initial kinetic energy, gives us the work which has been done on it, right? Or we can say the change in kinetic energy gives us the work done on the body. The work done is equal to the change in kinetic energy of an object. So let us convert the velocities into meters per second, or in SI units. So 30 kilometers per hour has been converted into 8.33 meters per second. You can see we have multiplied 1000 to convert it into meters and divided by 60 into 60, so that it gets converted to per second. And similarly we find out the final velocity also in SI units. It comes out to be 16.67 meters per second. Now we find out the initial kinetic energy. Initially, the car was moving at a speed of 8.33 meters per second. So half m u square, u was the initial speed, right? Initial velocity, half m u square will be this value 52041.68 joules. So this we get as kinetic energy initial. Similarly, we find out the kinetic energy final. Once again, half m times v square, right? Half times mass into velocity square. This once again gives us a value for kinetic energy, which is the final kinetic energy. And now the change in the kinetic energy has been brought in it by the work done on it. If a particular body was possessing some kinetic energy, if some work is being done on it or energy is being transferred to it, its kinetic energy must increase. Or if we find out the change in kinetic energy, we can get the amount of work which had been done on the body or the energy which had been transferred to the body. So work equals change in kinetic energy. We have used the delta sign to show that it is a change in kinetic energy. So a change in kinetic energy is the final kinetic energy minus the initial kinetic energy. And after we do this, we get the value as 156375 joules. So this is the value we get for the work done, right? So you can see the initial energy of the car was something around 50,000, and then when a work of almost 15,000, almost 156,000 joules had been done on the body, the energy of the body increased, right? Energy of the body increased by that amount, and now that energy was the kinetic energy itself. So remember this statement, change in kinetic energy always gives us the work done on the body or the energy which has been transferred to the body, right? So an energy, if some energy is transferred to the body, its energy must increase. And what is the energy which it has while it moves? It has kinetic energy. So let us talk about the next form of energy, next form of mechanical energy, which is the potential energy. Now to understand this, let us do one experiment. Take a rubber band, hold it at one end and pull it from the other. The band stretches, right? The band stretches, right? So now release the band at one of its ends. What will happen? Obviously, after releasing from one end, you will get hurt, but still observe the motion of a rubber band. The band will tend to regain its original length, right? If you stretch a rubber band and you leave it, it will try to regain its original length. And obviously, the band had acquired some energy in its stretched position, or else if we had stretched it to certain extent, how can it come back automatically when nothing is acting over it, no force is acting over it to give or transfer it energy, no energy is being transferred to it, no kind of a kinetic energy is being given to it, right? and there is no object which is pulling it towards the original shape, right? There is nothing helping it to come to its original shape. So how or from where does it acquire this energy, right? When the rubber band was stretched, how did the rubber band acquire some energy of its own so that it could come back to its original shape once it is released, right? Once the rubber band is released, from where does this rubber band acquire energy to come back to its original shape? And this can be explained like this: the energy gets stored in the rubber band due to the work done on the object, which is the rubber band, right? Here what happens is, when you pull the rubber band, you are actually doing some work on it. When you pull the rubber band, you are actually doing some work on it, right? Because you are applying force in this direction and the displacement is along the same direction. So when you are doing some work on it, you must be transferring some energy to it, right? You are doing work on the rubber band, so you are transferring energy to the rubber band, and this has been stored in the rubber band in the form of certain energy. So the energy transferred to an object is stored as the potential energy if it is not used to cause a change in the velocity or speed of that object. What we have done, we have stretched and kept it at that place. We were not moving it, we are not giving it a velocity or a speed, right? We were not making it move, we were keeping it at a standstill position, and due to that stretching, potential energy had been stored in it, or now it had potential to do some work on its own once it is let go. So you transfer energy when you stretch a rubber band, and what is the energy that is getting stored in it? It is called potential energy. So you can see this energy is stored as potential energy. So the potential energy possessed by the object is the energy present in it by the virtue of its position or configuration. As you can see, due to the change in its configuration, we have stretched the rubber band. Some energy was stored in it, and so once it was let go of, or once it was released, it could do work on its own to come back to its original position. Let's do one more experiment to see what actually potential energy means. So lift an object through a certain height, right? You are lifting an object to a certain height, and now the object can do work on its own. Don't believe me? Once you let go, once you just leave the object, once you leave the object from above, doesn't the object come to the ground on its own? Right? It comes to the ground on its own when no one is pushing or pulling it. Right? It begins to fall when released, right? It begins to fall when released. This implies that it has acquired some energy when it is raised to a certain height. So if raised to a greater height, it can do more work, because the height which is falling through is more, displacement is more, so work done will be more, right? So you can see, if raised to a greater height, it can do more work and hence possesses more energy if it is lifted to a greater height. So from where did this energy come? From where did it get the energy? when you lift up the object, you are actually doing work on it. And how are you doing work? You are lifting the object up against the force of gravity, right? And you are applying a force equal and opposite to that of the weight of the object, right? You are lifting the body up with the force equal to the weight of the object and doing some work, F into the height, right? And this energy, this work done on the object, is getting stored in the object, is getting transferred to the object and being stored as potential energy. And once the object is let go of, the object will do work on its own due to the energy it has stored in it. If work is being done on the object, it stores the work as potential energy. Due to this possession of energy, it can perform work on its own by falling down. The higher you lift it, the more potential energy gets stored in it, and the more work it can do by falling down. As I told you, if the height which through it's falling down, the h is more, so F into h will be more, or work done will be more, right? And the energy which it has is now getting transferred to the work done by the object. And you can see an object increases its energy when raised through a height, right? When an object is on the ground, even if you let it go, it will not do any work. But when you raise it to a certain height, it will fall, or it acquires certain energy when raised to a certain height. This is because work is done on it against gravity while it is being raised, as I told you. The energy present in such an object is the gravitational potential energy, or as we are doing work against gravity, the energy which is stored in it is due to the work against gravity only, or due to gravity, energy is being stored in the block when it is moved to a height. And that is why this energy or this potential energy is called as gravitational potential energy, because this happened due to the gravitational pull of the earth. So the gravitational potential energy of an object at a point above the ground is defined as the work done in raising it from the ground to that point against gravity. When the object is being raised to a particular point, the work done by the lifter to take the body to that point at the particular height, this work done is called the gravitational potential energy, because the same work is being stored in the object as gravitational potential energy. So let us now find the expression of potential energy as we had found in kinetic energy. So let us find the expression for potential energy as we had done in kinetic energy. So potential energy has been defined as the work done on the body to lift it up to a particular height, right? So if an object is applied a force F and it has been raised to a height h, we can calculate the work done as F into h. But what is F? F is nothing but equal to the weight of the body, right? F is the force which is applied equal and opposite to the weight of the body to lift it up. So its value must be equal to mg itself, or mass into acceleration due to gravity, times the height. Therefore, gravitational potential energy, or rather potential energy EP, can be defined as mgh, mass times acceleration due to gravity times the height, right? This is the expression for potential energy, or rather the gravitational potential energy. So let us use this formula to solve a question. Find the energy possessed by an object of mass 10 kg when it is at a height of 6 meter above the ground. Now when the object is at a height of 6 meter, that means it has some energy within it, it has some energy stored within it, because if it is released from that 6 meter height, it will fall down. That means it will do some work on its own. Therefore, the energy possessed by the body would obviously be potential energy. So we can find out that energy very easily. EP, or potential energy, is mgh, mass times acceleration due to gravity, given as 9.8 meters per second square, times the height 6 meters, which gives us 588 joules. And here you can see we have calculated the entire thing in SI units, so we get the answer in SI units itself. It is joules. So let us now consider the paths in which an object is taken to a height h, and let us see, does the amount of energy stored in that body change when it is taken to the height of h by different paths? Now the first path which is used is directly taking the body up, right? The first path is directly taking the body up to a certain height h. And now what is the potential energy stored in that body? It is mgh, right? Potential energy stored in that body will be mgh. Now let us talk about one more path, a complicated path. You can see body is first taken up, then towards right, then up again, then towards left, and once again up. Or it has been taken to the same height by following a different path. Now will it have the same potential energy or a different potential energy, because it had been moved through a longer distance? Now if you compare the potential energy by letting the object go, you will see both the objects fall straight to the earth, or they cover the same height while they fall, or they are doing the same amount of work while they are falling, right? So even if an object is taken by curved paths to the same height, the work or the energy which is getting stored in the body is same, as long as it is being taken to the same height. And why is it so? We can compare the potential energy as the energy which as the work done which the work done which is applicable on the body when it falls down, right? The amount of work which the body is doing while falling down is actually the stored energy in that body itself, right? The amount of energy stored in the body will be equal to the work done by the body in coming down, right? So even if the body is taken by different paths to the same height, the potential energy for any case would still be mgh, right? So remember, for the same heights of different bodies, potential energies would be same always. Or you can say potential energy is path independent, right? Potential energy is path independent. So let us solve one more question. An object of mass 12 kg is at a certain height above the ground. If the potential energy of the object is 480 joules, find the height at which the object is with respect to the ground. Now an object is having a mass of 12 kg and it is having a potential energy of 480 joules. right? That means it has been taken to a certain height and therefore it is having some potential energy. Now if it is taken to a greater height, its potential energy must increase, and therefore the potential energy, as it is non-zero, it is actually at certain height from the ground, right? So let us find out that height. So our given quantities are mass equals 12 kg and potential energy is 480 joules. So we know that potential energy is mgh, right? Mass times acceleration due to gravity times height, and g has been given here as 10 meters per second square. So let us put all the values we know in the equation and see which is the unknown quantity. And you can easily see, we know potential energy 480 joules, mass 12 kg, acceleration due to gravity 10 meters per second square. The only unknown quantity is the height. So by doing simple algebraic calculations, we can find out h by dividing 480 joules by the multiplication of 12 into 10. 480 joules by 120 kg meter per second square, or 480 joules by 120 Newton gives us 4 meters, and we have got the quantity in SI units as we are doing calculations with SI units only. So you can see height we have got as 4 meters. So you can easily say that the object is at a height of 4 meters, or the object has been taken to a height of 4 meters because it is having a particular amount or a specific amount of potential energy, right? So in this class we have looked at what is kinetic energy and its formula, potential energy and also its formula, and we have found out that potential energy is independent of the path in which an object is made to travel to a height. For better understanding of these topics, you can always log into Webcoach, and you should always go through your school textbooks and the NCERT book, and for further practice you can always go for different books of the TMH group. So thank you.